Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is April 3rd, 2017. The title of this lecture is Gasoline Piston Engine Compression Explained. This will be a two-part video lecture. In gasoline four-stroke piston engines, 4 piston stroke cycles occur to complete one duty cycle. Air and fuel intake on the piston downstroke, compression and spark ignition event on the upstroke, power on the piston downstroke, and exhaust on the piston upstroke. So in a 4-stroke piston engine, 2 revolutions of the crankshaft occur for every 1 power stroke. In gasoline 2-stroke piston engines, 2 piston stroke cycles occur to complete 1 duty cycle. Air and fuel intake, power, and exhaust on the piston downstroke, compression and spark ignition event on the upstroke. In a 2-stroke piston engine, 1 revolution of the crankshaft occurs for every 1 power stroke. 2-stroke gasoline piston engines are common with string trimmers and chainsaws. Right before the very end of the compression stroke, a spark ignition event is required in regards to gasoline piston engines. This is because gasoline is a very volatile fuel compared to diesel or kerosene jet fuel. In gasoline piston engines, compression is used to raise the temperature of the air-fuel charge to just below auto-ignition temperature of gasoline. Compression in gasoline piston engines can be thought of as an air-fuel heating system so that a thorough and complete combustion of the air-fuel gasoline charge takes place. Auto-ignition temperature is the temperature at which the compression itself will raise the temperature of the air charge to a high enough temperature to ignite the fuel without the need for spark ignition. Since gasoline is so volatile compared to diesel and kerosene, there is a limit at how high the compression ratio can be before an auto-ignition condition occurs and causes the gasoline to explode instead of burn smoothly. This explosion of the gasoline is known as detonation or knock. On modern automobiles, anti-knock sensors linked to the exhaust gas recirculation EGR valves regulate combustion under higher compressions to prevent detonation. Octane in gasoline has nothing to do with the amount of energy in the gasoline, though it slows down the flame front speed of gasoline under higher compression to prevent detonation or knock. Gasoline flame front speed is measured at an industry accepted value of 100 feet per second. On automobiles made after 2008 to 2010, the issue of too low octane and higher compression engines is no longer a concern due to the technological advancement of electronic anti-knock sensing linked to the EGR valves. Modern and cutting-edge automobiles made after 2010 have compression ratios around 11 to 1 to 11.3 to 1 and allow for very thorough air-fuel gasoline heating to occur, allowing for near complete combustion of the air-fuel gasoline charge, allowing a maximum potential BMEP to be reached when operating at maximum brake horsepower output. In regards to diesel piston engines and turbine engines, only air is initially compressed many times higher than gasoline compression ratio piston engines. The extreme compression ratios of 22 to 1 or higher in turbine engines and between 17 to 1 and 22 to 1 compression ratios in diesel piston engines cause the air itself to reach ignition temperature by the compression itself. This is known as heat of air compression piston and turbine engines. Only on initial startup is a glow plug or spark igniter needed on heat of air compression piston engines. After the compression is reached to its rating, then the auto ignition cycle kicks in, causing the heat of the compression of air to ignite the fuel. So in a diesel heat of air compression piston engine, only air is drawn into the intake stroke and compressed to 20 to 1 compression ratio. This causes the air to increase in temperature to as high as 900 degrees Fahrenheit in the absence of fuel. That's pertinent to the diesel piston engine, and on turbine jet engines, the heat of air compression tends to increase the air temperature to about 13 to 1400 degrees Fahrenheit. Right after the very end of the compression stroke, instead of a spark, diesel fuel is injected into the high temperature and high pressure oxygenated air, causing ignition to occur, absorbed at the start of the power stroke, resulting in power. Since diesel only burns at 6 feet per second flame front like kerosene jet fuel, these two fuels can only be used in heat of air compression engines, since these fuels are closer to oil and thus not as volatile as gasoline. Slow burning low volatility and cooler combustion temperatures represent diesel and kerosene jet fuel compared to gasoline. The turbine engine essentially does the same thing, but all 4 cycles occur at the same time, whereas in piston engines they occur at different times. Turbine engines operate on constant pressure combustion, whereas piston engines operate on constant volume combustion. Both are auto-ignition heat of air compression engines. The diesel 4-stroke piston engine reaches maximum torque at very low RPM, making it ideal for heavy payload transport. The turbine engine has both high torque and high RPM combined. The common denominator is that the high braking effective pressure in both engines exerted against their piston or turbine results in much higher torque output compared to gasoline combustion engines. In both the diesel piston engine and turbine engine, auto-ignition is the primary source of ignition, and that is caused by compressing the air charge to extremely high compressions, causing the air itself to increase in temperature and cause combustion to the diesel or kerosene fuel when introduced into the high pressure, high temperature oxygenated air, resulting in combustion and thus power. In a gasoline piston engine, the fuel is already so volatile that if heat of air compression was implemented to ignite the gasoline instead of a spark plug operating at lower compression, a literal explosion of the gasoline would occur during each power stroke, which would eventually lead to engine parts damage and failure. Even with anti-knock sensors linked to EGR valves, there is a limit as to how much compression ratio can be implemented in a gasoline piston engine. The reason why the compression ratio is so much higher in gasoline piston engines made in 2015 compared to 1995, 11.3 to 1 compared to 8.5 to 1, is because of the advancement in emissions reductions technology. When the proper materials are developed to hold up to higher compression ratios in gasoline piston engines, then a much higher compression ratio can be implemented, as is the case with late model automobile engines. At 11.3 to 1 compression ratio in gasoline 4-stroke automobile engines, the air-fuel gasoline charge is reaching close to its auto-ignition temperature prior to the spark ignition event. This results in little or no unburnt gasoline at the time of combustion, reducing and even eliminating unburnt gasoline emissions. The power lost to keep the engine running is known as friction horsepower. This includes the power lost to overcome compression, friction of engine moving parts, overcoming valve spring pressure, rotating camshaft and timing belt, and powering the intake and exhaust strokes as well. More compression also requires more power lost to keep engine running. It cannot be factored into the usable power output or brake horsepower. However, if a high enough compression is reached, then a more thorough and complete combustion at the air-fuel gasoline charge will occur, allowing for maximum BMEP potential when engine is operating at its maximum torque output. The auto-ignition temperature for gasoline is around 530 degrees Fahrenheit, and many late model 4-stroke gasoline piston engine compression ratios will cause the air-fuel gasoline charge to reach temperatures nearly 500 degrees Fahrenheit by the compression heating prior to the ignition or spark event. The advantages of increasing compression ratio to almost auto-ignition temperatures in gasoline piston engines is to facilitate a thorough and complete combustion of the air-fuel gasoline charge, thus allowing for maximum combustion of the given air-fuel gasoline charge, which will permit maximum BMEP output potential during the spark ignition event. Too much compression above the engine's design parameters will lead to explosion or detonation of the gasoline fuel and damage to engine parts, even with anti-knock sensing. Too little compression will lead to insufficient air-fuel gasoline charge heating and result in incomplete air-fuel charge combustion, reducing BMEP below given rating at certain RPM. This also will result in unburnt gas exiting the exhaust manifold. BMEP itself is harnessed from the burning of fuel and not directly from compression. Many people think increasing compression will lead to higher BMEP as a direct function, which is not correct. Compression's only purpose in a gasoline piston engine is to raise the temperature of the air-fuel charge to a high enough temperature so that as thorough and complete combustion of the air-fuel gasoline charge occurs. At 11.3 to 1 compression ratio in a gasoline piston engine equipped with anti-knock sensing, governed EGR valves, octane grade no longer is an issue, and close to or total combustion of the air-fuel charge of gasoline will occur. This results in higher BMEP during each power stroke compared to lower compression ratio gasoline piston engines, since close to or all of the air-fuel gasoline charge is burned, allowing for as much BMEP to be released during the power stroke. This now ends part 1 of this lecture, and I'll see you in part 2.